Welcome everybody. Just to make sure you're in the right spot, you're in for the Xenpwn Breaking Paravirtualized Devices with Felix Wilhelm in Mandalay Bay, GH. A couple things, housekeeping, you probably heard these before. Stop by the business hall located in Bayside AB during the day and for the welcome reception from 1730 to 1900 tonight. The Black Hat Arsenal is in the Palm Foyer on level 3. The Pony Awards are in Mandalay Bay, BCD at 1830. And don't forget to put your phones on vibrate. Thank you much.
Okay, hi everyone. Welcome to my talk, Xenpwn Breaking Paravirtualized Devices. So before I start with the interesting content of the presentation, I have a short introduction slide about myself. So I'm a security researcher working at E&W Research, which is a small penetration testing company located in Heidelberg, Germany. I mostly concentrate on application and virtualization security, and recent published research mostly focus on two different areas, security appliances on the one hand side. So I did some research on Palo Alto firewalls a couple of months ago and on the FireEye malware protection system in the summer of last year, I think. And besides that, I'm mostly concentrating on hypervisor security, so low-level virtualization security. For that, the recent years mostly concentrating on the Xen hypervisor. Yeah, you can also find me on Twitter. I'm not that active, but I'm always happy about more followers. So the agenda for today's talk, I give you a short introduction what's device virtualization and what are paravirtualized devices. So the term paravirtualized devices comes from the Xen hypervisor, but as we will learn, it's the concept or the same technology is used in all the mainstream hypervisors. So even if the talk has Xen in the title or in the subject, this is not research that's completely focused on Xen security. Instead, it's something that's relevant for all virtualization platforms. And then I'll talk about a vulnerability type I concentrated on in my research, and that's a so-called DoubleFetch vulnerability. I didn't find them manually. Instead, I developed a tool for that, and the tool is called Xenpwn. And in the main part of the talk, I give an overview about the architecture of this tool and its design. I used the tool on a couple of hypervisors, so I will present my results on that. And then I have a single special bug, which I think is really interesting from a technical perspective. And we do a full exploitation walkthrough, including a full Xen breakout by exploiting this vulnerability. So that's like the last part of the talk. So starting with device virtualization. So at its core, basically, if you have a virtual system, you need access to virtual devices. This can be like a disk or network device or even like a serial port or something like that. And traditionally, you just used device emulation. So if you look at how QEMU works, older versions of VMware work, they basically take a really old and well-supported hardware device and emulate it in software. This has the advantage that your guest operating system, so the virtual system, does not need any special drivers because these old devices are supported by almost any operating system you can imagine. So you don't need special drivers, you can just install from the standard installation source and the system will work. And for example, you have this really old floppy disk controller or something that's emulated in software. Now, when you look at the downsides of emulated devices, you have a couple of them. Most importantly, they're incredibly hard to implement securely and correctly. So if you look at like the vulnerability history of these device emulations, if you just look at the vulnerability statistics of the QEMU code base, you will see a lot of low-level memory corruption vulnerabilities because you are writing really low-level code, you're always writing it in C. It's kind of hard to implement that stuff correctly from a security perspective, but also correctly from like the features you want to support. And device emulation is kind of slow because you can't use any advanced features that were introduced like in the last years or something. Instead, you are implementing a hardware device that's kind of released somewhere in the 90s, re-implemented in software, so you don't have like a lot of speed or performance you can work with. And of course, all the advanced features you might be interested in probably are not supported by the original device, so you can't support them using device emulation. So what you're going to do, and what every mainstream hypervisor is currently doing, is you use paravirtualized devices. And the idea of this is that you have specialized device drivers that are optimized for use in virtual systems. So you still support emulated devices, at least most of the hypervisors still support them. But if a special device is running in the guest operating system, I think my mic has, if a special guest driver is working in the virtual system, then instead of using the emulated devices, you're using the paravirtualized devices. The term paravirtualized devices is kind of interesting because Xen also has a concept called paravirtualized domains. So they are kind of related, but they're not similar. So even if you have like hardware virtualized domains, so hardware assisted virtualization in Xen, it will still use paravirtualized devices. And the same holds true for like Hyper-V and VMware. And if you look at how these paravirtualized devices are actually implemented, you more or less always have this same architecture. So it's a split driver model where you have a front end that runs in the guest system, so in the virtual machine, and you have a back end. And the back end runs in the management domain. So in Xen, it would be DOM0. On Hyper-V, it would be like your VM host, or your privileged domain or partition. And on KVM, it would simply be your host system. And so all these hypervisors use basically this model. They call it differently. So on Xen, it's called backend and front end. On Hyper-V, it's called virtualization service client and virtualization service provider. And KVM uses the virt.io mechanism, and virt.io talks about devices and drivers. But if you actually look how they are implemented under the hood, they are kind of similar. So it's an interesting area to look at. And one important feature of this is that all these paravirtualized devices are implemented on top of shared memory. And the reason for that, of course, is that you have a really great performance. So you don't have to copy your buffers a lot around if you just share memory between the virtual domain, so the virtual system, and the host system. Because, of course, if you have like a virtual network card, at some point the data the virtual system puts inside the shared memory has to end in the buffer of the network card. But if you use shared memory, you have a lot of less copies than if you would do something like socket-based message passing or something like that. It's also really easy to implement because your hypervisor already includes all this memory mapping stuff. So simply creating a shared memory mapping between the virtual machine and the hypervisor is not a lot of code. And if you are really fancy, you can actually try to implement completely zero copy algorithms. So like you never have to move buffers around in memory, which leads to quite high performance. Of course, simply working with shared memory addresses or spaces wouldn't be very comfortable to a developer. So there are kind of message protocols implemented on top. And for Xen, Hyper-V, and KVM, these are just standard ring buffers. So you start filling at the beginning, and then you go around and have like dedicated message slots. There's implementation differences if you are implementing these shared memory mappings constantly. So for Xen, you have this grant table, which is more or less constant after the virtual machine boots up. Or if you create them on demand, so while your paravirtualized device is working, you could say, hey, please map my memory at that address in the management domain. So this is kind of an overview about how these paravirtualized devices work. Now the question is, if you look at these features from a security perspective, you will see it's a really interesting attack surface because this backend runs in the privileged context. So it either runs on the host system or in the management domain. And what is important for Xen or Hyper-V, if you own the management domain, you basically own the whole system. So it's not exactly like you're not exploiting the hypervisor itself. Instead, you're trying to exploit the backend that operates in the management domain. And if you get code execution there, it's basically game over. So you have this communication between the front end and the back end, and that's a trust boundary. And then you have like a lot of low-level code again. Because, so you have this ring buffer, and on top of that, of course, you have protocols. And these protocols are more or less device-specific. So like the network backend driver will speak like a different high-level protocol than, for example, the disk backend driver. And all these protocols are attack surface. The code that passes these protocols is again implemented in C. So you have like all the normal low-level vulnerabilities you also see for like network daemons or so. From like a pure security perspective, if you say your guest system is untrusted, then all this backend code operates in exactly the same environment than, for example, a network daemon. Because basically someone untrusted can send arbitrary data over this shared memory interface. And a couple of bugs released in these backend interfaces. So for example, the KVM disk backend had a heap-based buffer overflow that was disclosed in 2011. And it was just last year a really interesting buffer overflow in the Hyper-V storage backend, which is also interesting because it was internally discovered by a Microsoft researcher who got credit for that in a Microsoft advisory. So that was kind of an interesting vulnerability release. So now the question is, why aren't there more than these bugs, or why don't we see a lot of more vulnerabilities released in this area? And it seems to be that this code isn't as scrutinized as emulated devices. There are a couple of reasons for that. I think one of them is that all this code is device and hypervisor specific. So you're not working with like standard stuff. Instead, if you want to attack like the KVM virt.io backends, you have to understand how virt.io works, how the different devices work, and then even like sending fake messages is not completely trivial because you have to write your own kernel module and stuff, so it's kind of a bit of work, and it's always target specific, so it's not something you can generically target to a different hypervisor. And it's much harder to fuzz than simply emulated devices. So for an emulated device, you have like this I/O port communication stuff. So you're just writing to I/O ports. Maybe you have some memory mapped I/O interfaces or something like that. For a paravirtualized device, you often have like a complex protocol that's stateful. So you have to like build up a connection and stuff. And of course, if your virtual disk driver misbehaves, it's kind of, so you can assume that your virtual machine won't survive that long. So fuzzing this isn't like as trivial as just like executing a, I don't know, bootable disk and fuzzing I/O ports. I still think this stuff is a very interesting target because nowadays, if you look at how device emulation is done, so if you look at QEMU or if you look at the VM worker process, which is responsible for device emulation in Hyper-V, you will see that this is often done in user space. And it's done in user space in a heavily sandboxed environment. So normally the VM worker process under a modern Hyper-V environment has really heavily restricted permissions. So even if you exploit it, you need another bug to completely compromise the host system. QEMU is sandboxed by using SE Linux or something like that. So again, you need another privilege escalation. On the other hand, if you look at these paravirtualized device backends, because they're really performance critical, they're implemented in the kernel for higher performance. So if you look at the device backends or the network backends of Xen, KVM, Hyper-V, they are all kernel modules or kernel drivers running inside the kernel space of the management domain. And this means if you have code execution, it's an instant game over because then you compromise the whole system. And these paravirtualized devices are also becoming more and more important. So if you compare the performance of different hypervisors currently, the main performance difference you will see is actually the difference of these paravirtualized devices. So if you compare like the network traffic you can put through a VMware machine and a Hyper-V machine, the difference you will see strongly depends on the performance of these paravirtualized device drivers. So this means they implement more features, more optimizations, so this code base is growing and not shrinking or not getting sandboxed. You also have like a lot of more device types, so for example USB, PCI, 3D acceleration and stuff like that. And And then you have an interesting future development. So if you look at Hyper-V, they actually introduced generation 2 VMs, which completely remove emulated devices, because they noticed this is a kind of an interesting attack surface. So if you completely remove emulate device support, you only have the paravirtualized devices to attack. So what's the goal of my research? Basically, I wanted to find an efficient way, so efficient vulnerability discovery in paravirtualized devices. And what do I mean with efficient? The idea was I didn't want to spend too much time in IDA or reading the source code. Instead, I wanted to have some kind of automatic tool that helps me identifying vulnerabilities. And my core idea was basically that you have, or that nobody ever presented any kind of research on the use of shared memory in the context of these paravirtualized devices. What's interesting about shared memory, and there's a certain bug class that only affects shared memory, and that bug class is called a DoubleFetch. So what are DoubleFetch vulnerabilities? They're a special type of time of check to time of use vulnerability that affects shared memory. So like a simple definition would be you have a same memory address, and the memory address is accessed multiple times out of a privileged context, so from the backend, but the validation of the accessed data is missing at least once. So for example, the backend reads an integer out of a shared memory section, and it fetches the value once, checks that it fit into an upper boundary, and then sometimes later it checks or it fetches the value a second time. But it doesn't include the check again, so the upper boundary check. And then you have a classic time of check, time to use bug, so you can simply raise or try to exploit the raise condition to flip the value in between these two fetches. The cool thing about DoubleFetch vulnerabilities is, so this vulnerability class can lead to a lot of powerful exploit primitives depending on the kind of bug. Because sometimes you can just like skip over a certain check, so this can lead to arbitrary reads, arbitrary writes, buffer overflows, or even like direct control over the instruction pointer, as we will see later on during my demo. So some history, like the term DoubleFetch was actually coined by Fermin Zerner in 2008 in a blog post on the Microsoft Research blog, I think. But the bug class itself is well known before that. It's just like the term DoubleFetch that was introduced there. The first wave of research on this bug class was published in 2007 and 2008, so there was a really good paper at Usenix 2007 on exploiting concurrency vulnerabilities in system call wrappers, which talked about this kind of issue. And then there was the presentation at CCC and the famous FRAG paper by Twiss and Escriacu, where they also talked about these bug types. The first example of a bug that actually fits this DoubleFetch paradigm is a send message Linux bug which allowed privilege escalation in 2005. So I also have an example for this one. So in this kind of shared memory interface is like the user space, because if you have like user space kernel communication, then you can think about the user space as a shared memory interface, because the kernel can access it, but at the same time the user space can still manipulate it. And basically, the problem is that you have two fetches to this UCM len variable. So you have this get user wrapper which copies data out of the user space, and at the first marked line it's copied into the UCM len variable, and then it's used to perform a heap allocation, or depending on the size, it's a heap allocation or it's stored on the stack. And then a couple of lines later, they fetch the value again at the same address and use it as the size parameter of a copy from user call. And of course, an attacker can simply flip the value in between these two calls, and then you have a trivial stack-based overflow or heap overflow, depending on the size your original pass. So this is like the first example of these bugs. Now, a couple of years later, there was this really interesting research. Bochspwn, it was published by Yoru and Ginvael, and they released a paper identifying and exploiting Windows kernel race conditions via memory access patterns. And the idea was basically they wanted to identify these DoubleFetch vulnerabilities by using an extended version of the Box CPU emulator to trace all memory accesses from kernel to user space. So they look at every memory access from kernel to user space, and if they see multiple memory accesses to the same address in a short time frame, they might have a DoubleFetch vulnerability. So Bochspwn resulted in a significant number of Windows bugs. So they only looked at local privilege escalations in the OS context, so kernel vulnerabilities. They also won a well-deserved bounty for most innovative research. But interestingly, they also released like the whole tool as open source, but nobody really followed up on this. So you don't see a lot of follow-up research using that tool. And they will also release like a really detailed white paper that contains an analysis when these double fetches become exploitable. And to make it short or to summarize it in one sentence, if you have a multi-core system, so like the system has multiple CPU cores available, then even if your race is extremely short, these type of bugs are exploitable. Which is perfectly fine for my use case, because normally if you are operating in a virtual machine, you probably have more than one CPU core available. As you might notice from the name of my talk, Bochspwn was the main inspiration for this research, and they found a lot of interesting bugs. So one example of a vulnerability they found, and this is in the Windows kernel, so we don't have source code available for this, but you can see in the first line, so the EDI register points into user space. So they go to the hex offset 80 of EDI and fetch a value into ECX. They then use this ECX value as an argument to probe for write. And basically what probe for write is, it does check if that's a valid user space pointer. So if the kernel should write into there, or if it's an address that's pointing into the kernel space, because then you could have triggered memory corruption. So they have this check to probe for write, and after that they call memcopy with the same user space address again as a length parameter, as a destination parameter, I'm sorry. But the problem, of course, is they perform a memory fetch a second time. So between line 1 and between line 9, you have like this race condition again, where you can flip a different value in there and perform arbitrary memory corruption. They also demoed that this is sufficient to get privilege escalation. So the idea of Xenpwn now is to adapt this memory tracing approach that is used by Bochspwn, but now uses to analyze paravirtualized device communication. You might ask, why don't we simply use Bochspwn? Main problem is that Bochspwn is really, really slow, because like the Box CPU emulator is already slow. If you add additional instrumentation, it becomes even slower. And it's a passive overhead, so you have this for every memory access, not only memory accesses we are interested in. My main problem when I tried to use it was basically compatibility issues. So you are not even able to run Hyper-V inside a box, at least at the point in time when I tested this. And they used a basic approach to just dump their memory traces into a text file, which also does not scale if you want to do like long-running traces. So my idea was I wanted to implement the same technique or approach, but implement it on top of hardware-assisted virtualization. So and this is the architecture I landed on. And basically the core idea is you have nested virtualization. So you have a level 0 hypervisor, and on top of this you have another hypervisor running the level 1 hypervisor. And the level 1 hypervisors are actually target, so we look at communication of virtual machines running under this level 1 hypervisor, and all my tooling runs as the management domain in level 1. So the Xenpwn architecture, the advantage of this architecture is that you don't require any modification to the hypervisor, so I can just use the off-the-shelf Xen hypervisor, and if I write stupid code, so if I write bugs, you don't crash the whole system. I mean, if I would modify the Xen hypervisor and I would introduce bugs, it would probably have a lot of impact. So what I need like this one interface to talk to the level 0 hypervisor and to somehow perform memory access tracing with this. And one of the core components I use for this is libvmi. And libvmi is a great library for virtual machine introspection. And it's more or less hypervisor agnostic, so you can use it with Xen or KVM. And it's a user space wrapper. So at the end, you just have like a simple C user space API. And it allows us to read and manipulate the guest CPU state. So I can look into the memory, I can look at CPU registers, and even manipulate them. And more interestingly, the Xen version supports a feature called memory events. And memory events allow me to trap on an access to a guest physical address. So when every time my nested hypervisor or its virtual machines access a certain guest physical address, this will trigger an EPT violation. So it's implemented using extended page tables. It will trigger an EPT violation and a VM exit, and my tooling gets controlled, so my handler gets called, so I can analyze what triggered this memory access and if it's interesting. So with this feature, we can kind of easily implement memory access tracing. We basically find all shared memory pages, then we register memory event handlers for every of these shared memory pages, and whenever an EPT violation is triggered, so whenever we see something, we analyze this memory event, extract all the needed information, and then store it somewhere in our trace storage with an analysis algorithm that later on tries to find DoubleFetch vulnerabilities or whatever else we are interested in. The trace collector, as I said before, it uses libvmi to inspect memory and to identify the shared memory pages. This is interesting because it's the only target-specific code. So I can target the Xen hypervisor, I can target Hyper-V, I can even target the Chrome sandbox, for example. I just have to write code that is able to identify a shared memory page that kind of is relevant as a trust boundary. Depending on how this is implemented, you basically have to walk through data structures inside the virtual machine to parse like the physical memory addresses. If it has identified this shared memory page, it then registers a memory event handler, so we get notified whenever someone accesses these pages. And then the callback handler does the main work. It analyzes the access, it disassembles the instruction using the capstone library to identify what kind of memory access it is, and then stores all these informations. So the callback handler basically looks like this. So in my case, I'm only interested in accesses from the privileged domain. I don't want to find double fetches in the front end because the front end isn't privileged. Instead, I'm only looking at the back end. So first of all, we have to extract the domain ID. Then we look if it's the privileged domain. If that's the case, we further analyze it. If we have never seen that instruction before, we disassemble it to store data about the instructions. And at the end, we just create a trace entry for this memory access and then let the VM continue. So the question is where to store these traces. So as you can imagine, they become quite large. And so you need to have a fast persistent storage with minimum overhead. You want to have efficient compression because then you can store longer traces. And luckily, there's a tool that kind of fulfills this requirement. It's called ZeroTrace. It's developed by the Open Operations System Group at the Karlsruhe Institute of Technology. And ZeroTrace is basically designed for full system memory tracing. So it's a storage where you can store complete memory traces with the memory content that's written. So this is kind of interesting for replaying of virtual machine activity. It's optimized on really highly efficient communication over shared memory pages again. It's written in C++. You get a client library you can use from C. And then you have this daemon running besides it that's responsible for all the trace entries. So it's kind of like a special database you can imagine. The cool fact about this is that it has a special compression algorithm that's optimized for memory traces. So I can put data in there and it's get compressed with an incredibly high rate. So I don't need a lot of space. I think this tool is quite interesting. And you should check it out. I also think it's kind of useful for stuff like heap visualization or maybe other logging stuff that requires high performance. Now the question is, what kind of entries do I store inside there? And basically what we're doing is we have this cycle count, which is just counting upwards. Then we have an instruction pointer. So that is the instruction that's responsible for the memory access. We have the memory address itself. and we have the size and the type of this memory access, so we know it's a read or if it's a write access. And then for every unique instruction, so a single instruction will be responsible for a lot of memory accesses. So only for every unique instruction, we also store like the instruction bytes we can later look at, as well as the module name. So I'm able to kind of perform offline analysis to find out which module was responsible for this check. So kernel module or Windows kernel driver. And if we have these trace entries stored, then the DoubleFetch algorithm, so to identify DoubleFetch vulnerabilities, is actually kind of trivial. So this is a bit of a simplified version, so I'm skipping over a bit of details, but basically you just like iterate through this trace file, look if it's a privileged access. If it's a privileged access and it's a read access, then we add this access to a map or a dictionary, and the first time we see an unprivileged access, which means we have a context switch, then we analyze our current state of the dictionary, and if we find multiple read accesses to one memory address, we probably have a DoubleFetch vulnerability. As I said before, this is kind of simplified. You have a lot of problems with false positive, false negatives, overlapping accesses and stuff. So if you're interested, you should look at the white paper that discusses this algorithm in a lot more detail. But this is like the core idea how I find DoubleFetch vulnerabilities. Now the approach has a couple of advantages as well as limitations. So the cool thing about this is you have a really low passive overhead. Like this nested virtualization doesn't introduce a significant overhead. The only thing that of course introduces overhead is this if actually accesses to these shared memory pages occur. Because for every access to a shared memory page, you will have a VM exit. So in the moment you enable tracing and perform disk activity, you will see the performance really suffers, but you can set up the whole system and configure it and target like which devices you want to look at, all with a very low overhead. So this is kind of interesting. The approach is largely target independent, so the trace collector and everything more or less stays the same. Only the stuff that identifies these shared memory pages needs to be adapted to a new target. And it's all user-space C code, or C++ code, so you can kind of easily extend it. Bad, as I said before, you have this high active overhead when you generate a lot of VM exit, and it relies on nested virtualization, so that's kind of unfortunate because nested virtualization on Xen is kind of supported. So if you look at the official Xen documentation, they say nested HVM on Intel CPUs should be considered a tech preview, and it should work reliably and with low overhead for many use cases. For me, it only really stably works for Xen on Xen. KVM on Xen works most of the time. Beehive on Xen also works kinda. Unfortunately, I wasn't able to get Hyper-V on Xen running, so I'm still trying to do that because originally I wanted to look at Hyper-V vulnerabilities. So I tested it on 3 different hypervisors. The first results for KVM are kind of, I was disappointed by that because you don't find any security critical double fetches in the backend. The main reason for this seems to be that the virt.io, so the Paravirtualized device mechanism used by KVM, is actually endian independent. So they support a guest operating system that's big endian while the host system is little endian. So every time they access the guest memory, they have this small access wrappers that basically just decide on the endianness. And of course, it's much harder to introduce double fetches if you have these endianness wrappers. As it turns out, if you actually start reading the virt.io code, there are other interesting issues that are not double fetches. So I have kind of a couple of disclosures going on, so hopefully I can publish a blog post about those. Beehive was kind of interesting because I only find one double fetch, but this one was kind of very interesting. They are still trying to patch it, so still ongoing disclosure process. But the Xen research is the oldest of those, and they have found 3 interesting double fetches, and all of them are patched, so these are the ones I want to discuss in detail. So the first one is kind of interesting. It's in the QEMU Xen disk backend. So this is one backend that's normally used if you just push like a normal file as a disk into your virtual machine. And they have this block interface get request function. And if you look at the lines highlighted, so the source pointer is pointing into shared memory. If you look at the lines that are highlighted, you can see 3 accesses to the source pointer and the field number of segments. So the one highlighted in red in the top, and then you have this if conditions, and after the if condition you have this assignment. So these are 3 memory accesses. My tool discovered there's a potential double fetch. And now if you look at the if condition, so it's an upper limit check. It checks that source number segments shouldn't be larger than n. And if these 2 lines actually would be compiled into true memory accesses, you would have a trivial buffer overflow, because you can manipulate source number segments in a way that when the memory is accessed the first time, it has like a really small value, but then after that you have this really big value, and then the for loop below that simply overflows. However, it turns out that if you compile this with normal optimization levels, so GCC 02 or something, then this if condition will be compiled into a single memory access. So this is interesting because it's a bug that is kind of trivial to see in source code. So this is classic double fetch, but is not exploitable for most production systems because of compiler optimizations. My tool discovered this bug because the first line highlighted in red isn't second memory access, so there are 2 memory accesses, but this one unfortunately isn't security critical. So this isn't really an exploitable bug, but it's still kind of interesting. The second bug I discovered is in the Blockback interface. And purely from an exploitation perspective, this is probably the most interesting one. So you have the segments array, and they access this last sect and first sector numbers. And they use it to calculate a number of sectors. And after they calculate this value, they have this if condition where they check the values are kind of harmless or lie in a valid range. And if you can flip the values in between this assignment and this highlighted if condition, then you can trigger out-of-bound read and write vulnerabilities out of this using the Blockback interface in Xen. So this is probably, if you want to exploit this in the real world, this is the most interesting one because the Blockback interface of Xen is widely used. However, my most favorite bug is in the PCI Pack interface. And this one it's not, you probably don't find a lot of hosts that are actually using this interface because it's only relevant if you have a virtual machine that, for example, has a GPU or something. So you have like a virtual PCE device inside the virtual machine, which happens, but it's not like the default setup. However, the bug is so technically interesting that it's still my favorite one. So you have this Xen PCI Pack do op function. And as you can see on the left-hand side, it's basically a big switch statement. And it doesn't look vulnerable at all. So if you just look at the C code, it doesn't do a lot. I mean, it calls into functions, but it's not really interesting. As it turns out, the op CMD, so op is a pointer into shared memory again. And now, if you look at the compiled version of this function, you will see really interesting behavior. Because so the op CMD value corresponds to the registers, so R13 plus 4, you can see in line 1. So this is like the correspondence in the disassembly code. And you can see in line 1, they have this comparison check where they compare this value with an upper limit of 5. And if the limit is large, or if the value inside there is larger than 5, they jump to the default case of the switch statement. So this is like a jump table, so it's a classic compiler optimization. But then you have, in line 4, you can see when they actually perform this jump, so that they use the value you choose as an offset into the jump table, they fetch it a second time out of the shared memory. So you can see in line 4, they have this move EAX, and they access the memory address a second time. And this is an awesome bug, because basically you can skip over the upper limit check in this jump table optimization. You can put an arbitrary value inside there if you win the race condition, and then you almost directly gain indirect instruction pointer control. So, it's interesting that this is a valid compiler optimization because the mistake in the source code is that the op variable or the op pointer isn't marked as volatile. So the compiler doesn't think it's possible that this value could switch in between 2 accesses. But still, I think not many people would actually discover this by looking at the source code. So this shows it's relevant to actually look at the binary when looking for these kind of bugs. Now, how to exploit this? And exploiting PCI Pack turns out to be an interesting challenge. So first of all, you have a really small ways because these two memory accesses are more or less directly behind each other. There are only two instructions in between. It turns out if you have a guest VM that has multiple cores, this is kind of simple to exploit because you don't have any negative side effects if you lose the race. So you just can try infinite times. And as you hopefully see in my demo, it normally works after like 5 seconds or something. So it's not hard to win that race. And it's incredibly simple to trigger. Basically, you send PCI read requests over this paravirtualized PCI backend and just flip the value of this opcmd parameter using XOR in a second thread. So by flipping it, you can manipulate this and then continue on. So it turns out you have an indirect jump. So you don't have immediate instruction pointer control, and you need to find a reliable offset to a function pointer. So you don't directly control in the instruction pointer. Instead, you need to find a function pointer that's interesting to you. The problem is normally Xenpwn Pack is a kernel module, so the load address will be random, so you can't point to arbitrary addresses in the kernel. You also don't know the virtual address of your backend mapping, so that's also random. So it's kind of similar to a remote kernel exploit. The approach I've chosen is that I trigger a type confusion to then get a write primitive, and from the write primitive on, I walk forward. This has some downsides, as I'll show later on, but it kind of works for me. So if you look at the code of Xenpwn Pack, you will see there's a second jump table that's generated for this. It's almost directly behind the jump table that's generated for the vulnerable function, and you can choose an arbitrary function pointer out of this jump table. So we can jump into an arbitrary case statement of the code shown in the upper right, I'm sorry. And if you look at the disassembly again of this function, you will see that they take the R13 pointer as the first argument and then call Xenpwn Pack attach. And this is interesting because normally if you jump into this case statement, R13 should be a pointer to Xenpwn Pack device structure, but now it's simply a pointer inside our shared memory region, so something we completely control. So now we have a type confusion where we can call Xenpwn Pack attach with arbitrary arguments. The first thing this Xenpwn Pack attach function does is it tries to lock the devlog mutex of the structure you pass in. So you can see the normal pointer you would normally pass would point to the structure you can see on the upper right, and there's like a mutex in there, and it tries to lock this mutex. And now we have the possibility to call Mutex Lock with a fake mutex structure, and at first, this doesn't sound too interesting, because if you look at mutexes, probably they just flip like the lock count or something, but it turns out the Linux mutex structure has a fast path that happens if the mutex currently is unlocked, and the slow path. So we need to trigger the slow path by manipulating the shared memory section in a way we have a mutex that looks like it's locked. If we look at the lock slow path, we can see they try to do an optimistic spin lock. We can make that fail. And if it fails, then they create a so-called mutex waiter structure. So this is a structure that will later on be waked up to try to get the mutex again. And if you look at how this works, so this mutex waiter structure is added to a linked list, the lock waitlist linked list. And by triggering this process, we can write the pointer to this waiter structure that lies on the local stack to an attacker-controlled location. So this is kind of an interesting write primitive. It's a write where, but not a write what. So we can write a pointer to attacker-controlled data, but we can't simply overwrite like a function pointer with an arbitrary value. So that doesn't work. Instead, basically, what we can do is we can insert like a faked list head structure. So we have this next pointer, and the next pointer will point to control data. So we have a double indirection in our write. Main problem of this exploit is that it's a one shot, so you are only able to trigger a single write. This is stupid because then PCI Pack, after that it's locked, it will never return, so you can't exploit this vulnerability multiple times. What I'm going to do is add a faked entry to a global linked list, which works quite well, but it requires that you know the kernel version of your target system, and it doesn't have CASLR, or alternatively that you find a different info leak in some other component. So this is like the downside of this exploit approach. And what basically happens, so the green stuff is the memory layout we put into our shared memory location, and we have this fake previous pointer that points to a global linked list inside the kernel. And after we trigger our override and after this Mutex Lock function is triggered, we get a memory layout that looks something like this. So you have this list head.next, then a pointer to this waiter structure. And the problem is, again, the waiter structure is kind of arbitrary junk, so we don't control that. And after that, if you follow the next pointer a second time, we are landing in our controlled data. So doesn't look too powerful. So we have a global data, so we need to find a global data structure because we need to know the address of its list head pointer. It shouldn't have new elements, so this list we want to override shouldn't be like dynamic, otherwise we get problems. And it needs to survive one junk entry because again, we don't control this waiter status. So when this list is walked, it should just ignore the waiter structure. So this took me a bit of time until I discovered something interesting, and it's hidden in one of the oldest files of the Linux kernel, I guess. It's the fsexec.c. You can see the copyright is from 1901 in this code, and most of the code actually looks like it's from that date as well. And it contains a global linked list inside the Linux kernel that's called formats. And formats contains entry for different file formats that are supported by exec. So if you execute an elf or a shell script or an out file, all these formats are stored inside this linked list, and they basically are the handler functions that are responsible for spawning the processes. And the cool thing about this list is that it's walked every time an exec syscall is called to load such an input file. And our junk entry will be skipped because they call try module get on our junk entry, which just doesn't make any sense. So it will just skip over our wait entry and then use our new data structure as like a as input or as variable for this loading of formats. So when we have this, we need to so getting to code execution is then kind of easy. So there's this load binary pointer inside this formats entries. We set this to our stack pivot, then we have like a normal kernel rob chain where we allocate executable memory, copy our shellcode there. We fix the original formats list. And then the next time an exec is triggered, or more or less when this is triggered, we can execute an arbitrary shellcode, like $shellcode. In my case, it's just a simple reverse shell. Normally, you would probably do something more complex because the management domain might not be network accessible. And then we just return to user space. The cool thing about like the kernel rob is kind of easy because inside the kernel, you have like infinite gadgets. So this is not the hard part of it. So I have a demo. It's kind of semi-stable, so I hope it will work. Otherwise, I show you the video I've made of it. So let me check. Here's my mouse pointer. So I'm now connecting to my vulnerable Xen hypervisor. Yeah. Now it worked. And you can see like the hypervisor itself has the host name Xen, while the guest system running inside there, so the unprivileged guest has the host name guest. And what should happen is that we see a shell popping up that goes from, so we see a reverse connection from the hypervisor to the guest. So you can see I can execute LSPCI, and this basically just shows me one of the virtual LSPCI devices I have. So this will hopefully work. Now this is the vulnerability or the tool that actually triggers the override. So this is the race condition. So on the right-hand side, I trigger this LSPCI call, while on the left-hand side, I try to trigger the overflow. So as we know, we have to execute this or to trigger this race condition, and we can see the LSPCI call is hanging, so that already shows that I've won the race. So now basically I have the first step of the exploit working. Let me check. And now I'm going to open a reverse shell listening here and do the sudo prepare shellcode, and hopefully, that's normal. My exploits are always shy. They work in the hotel room, but never on stage. So it didn't trigger correctly. I'm also more or less over time, so we do the quick backup. I have a video of it. So sorry about that, but now you can see if I'm able to put it on the screen. Check. So there it is. It does the same thing I just tried to demonstrate live, but only this time it's working. So you can see on the right-hand side, I'm triggering the LSPCI activity, and so the override pointer stuff tries to trigger the race condition. If LSPCI hangs, the virtual PCI backend hangs, we can see the override worked. Then I have a second user space utility which actually prepares the shellcode in the shared memory. So before I execute that, on the host system, everything that exec actually crashes, so nothing bad happens. But I just wait until LSPCI times out, open my reverse shell, and then do the sudo prepare shellcode on the left-hand side. You see reverse connection from the Xen hypervisor, and you can see I get a root shell on the Xen hypervisor. So this is a full breakout out of the virtual machine, and you get a root on the Xen hypervisor. Thank you. Just two final slides. I have Xenpwn is finally open source. I promised this a couple of months ago already. So find it on GitHub. It's actually still private. I have to look into GitHub and make it public, but that will happen immediately. Black Hat will release a white paper, which is also the master thesis I wrote on this. So this contains a lot of more technical detail on the whole work. So if I skipped about some details, please find them in the white paper. Future work, I want to look at Hyper-V and VMware. Also interesting might be other shared memory boundaries like sandboxes, and the question is what type of bugs can we find if we not only look at memory accesses, but also the full memory content that are accessed. Because this is kind of supported by my tool and also by ZeroTrace. So if you have any ideas how you could use that to find cool bugs, come talk to me. Thanks for your attention. Happy to answer any questions. Yeah, we have to take it outside because I'm already over time, so just find me somewhere in the hallway. Thanks.